Hello everyone, I am Dheeraj Madan from IBM Research India. Today I will be presenting our work titled Learning Hard Distributions with Quantum Enhanced Variational Autoencoders. This work is to be presented at NeurIP's workshop on machine learning and physical sciences. This is a joint work with my co-authors Anant Rao and Professor M.S. Santhanam from IISER Pune and Anupama Ray and Dhina Karan who are my colleagues at IBM. Here we attempt to solve the task of generative learning, which consists of the following. That is, we are given a bunch of samples xi's coming from a distribution pxx, and our goal is to model that distribution, meaning that we should be able to produce more such samples from the same distribution. One of the existing approaches for the same is that of variational autoencoders. Variational autoencoders are a family of models which essentially are based on a latent variable z, which comes from a prior, say pz, and essentially they try to model the likelihood p theta x given z given the samples from px. Now the way the variational autoencoder is designed is that it consists of two parts, namely the encoder and the decoder. The encoder essentially takes as input an x and produces a sample from the distribution q phi z given x, which is modeled as the approximate posterior. Given this sample, the decoder now tries to regenerate back x from the input z. And variational autoencoders attempt to maximize a twin objective function which consists of a reconstruction term and a KL divergence term. So the reconstruction term is defined as the expectation over qz given x log p theta x given z, and the KL divergence term, which is also known as the regularization term, tries to reduce the sort of divergence between qz given x and pz. So this essentially tries to ensure that the approximate posterior is somewhat closer to our original prior. So at test time, I will be sampling from my original prior a z, and then using that z I will be sampling x from p theta x given z. In our work, we essentially replace the decoder part of the circuit with the quantum circuit. Here we obtain a closed form expression for the class of distribution which we model through such a network wherein the decoder or the likelihood function has been replaced by a quantum network. Using the same, we show 2x improvement in fidelity on distributions which are obtained by sampling quantum states. We now use this particular model for the task of circuit compilation, right, which is the task of reducing the number of gates and the circuit depth in a given quantum circuit. Now our proposed model and results are as follows. So essentially we are modeling the likelihood distribution which is the decoder network as p theta x given z being modeled as so basically u theta z, which is a parameterized ansatz which acts on a state get 0 n, right. So here z is sort of an input which is first created which first produces a sort of a input state vector using a feature map, followed by a parameterized ansatz which produces a parameterized state, and then finally we make a measurement in the standard basis to give us the required distribution. Our main result in the paper is that modeling a likelihood network via this particular quantum circuit, this is equivalent to performing quantum circuit sampling starting from a mixed initial state. However, we have shown some good improvement in fidelity scores using our technique over and above classical variational autoencoders. So for example, on 8 qubit states which are obtained from random quantum circuits, we have shown a mean fidelity improvement by a factor of more than twice. And coming to the application part in terms of circuit compilation, we have shown that we can produce circuits which have much shorter depth and much fewer gate count than the original one. So we experimented with a family of circuits and we have shown that the number of C nodes is reduced by a large factor and however the distribution which we get by sampling is the same as the original one. So finally, for references, you can also look at the original works on variational autoencoders, and another work which uses the classical variational autoencoders for learning quantum distributions. Okay, yeah, thanks. That's it.